Okay, so welcome to this next video on strokes and excitotoxicity of neurons. Right, okay, so we are going to try and understand what ATP levels going down within our neuron is actually going to cause. And the important bit is going to happen in this axon terminal, basically. Okay, so let's just revise how resting membrane potential is maintained across a cell membrane. So overall, you have a high sodium concentration extracellularly, you have a low sodium concentration intracellularly, you have a high potassium concentration intracellularly, and you have a low potassium concentration extracellularly. Now, in all membranes, you have some channels which are permeable to sodium and which are always open. These are known as leaky sodium channels. So this is a leaky sodium channel. Okay, so I'll color this leaky sodium channel in orange. Now, you also have some channels which are always open, which are permeable to potassium. These are called leaky potassium channels. Okay, we'll color in leaky potassium channels red. So here are leaky potassium channels. Right, so these are the leaky channels, I'll just label them, leaky channels. Right, and basically what happens is that you always get some sodium moving into the cell through this leaky sodium channel. Okay, so you get at resting membrane potential. Actually, shall we discuss how resting membrane potential is built up? Okay, we will. Right, so initially what happens is that the plasma membrane actually is far more permeable to potassium than sodium. So there are far more of these leaky potassium channels than there are sodium. We will assume that at the moment our resting membrane potential is 0. So the electrical potential difference between these two compartments is 0. So they're both equal. So everything's neutral at the moment. So we're looking at truly how do we build up resting membrane potential. Now, initially, the movement of potassium out of the cell is going to beat the movement of sodium into the cell. Two reasons for that. The potassium gradient is actually bigger than the sodium gradient. The difference between the intracellular concentration of potassium and the extracellular concentration of potassium is bigger than the difference between the sodium concentrations. So the concentration gradient that's driving potassium out of this cell is bigger than the concentration gradient driving sodium into the cell. Okay. Secondly, I've said that the actual permeability of the membrane to potassium is greater than it is for sodium. Both of these factors mean that more potassium is going to leave the cell than sodium is going to come into the cell. So, you are moving a net positive charge out of the cell because the potassium ions carry a positive charge and the sodium ions also carry a positive charge. You're moving less sodium ions in than you're moving potassium out. So overall, you're going to move a few positive charges overall out. So now what you've done is you've moved a few positive charges out. And that means that because you've moved them out of the intracellular compartment, that makes the intracellular compartment slightly negative. So you've made this compartment slightly negative, you made the extracellular compartment slightly positive. Okay, now, this process is going to continue on for a few seconds, or however long. It probably takes much less time than that to actually reach an equilibrium. But what's going to gradually happen is that as you continue moving a net positive charge out of the cell, you're going to make the electrical potential difference across this membrane bigger and bigger. You're making the extracellular compartment more positive, and you're making the intracellular compartment more negative, which means the electrical potential of the extracellular compartment is going to go up, and the electrical potential of the intracellular compartment is going to go down. Okay, so the electrical potential difference across this membrane, which is the voltage from extracellular to intracellular, which means if I had a little man standing in the extracellular compartment measuring electrical potential, and he then moves into the intracellular compartment and measures electrical potential in there, how much different is the electrical potential on the intracellular compartment than the extracellular one? So what he would have to do is he'd have to take the electrical potential of the intracellular compartment, and he'd then have to subtract off what the original electrical potential that he was measuring, which was the electrical potential of the extracellular compartment was. Okay, and that's what is meant by this voltage across the membrane. Okay, so this is gradually getting bigger and bigger because, as I say, as you move a net positive charge out, the electrical potential of the extracellular compartment is getting bigger, and the electrical potential of the intracellular compartment is getting more negative. So this one's getting smaller, this one's getting bigger, which means this number is getting more and more negative. Now, these are positively charged ions we are moving here. Positively charged ions like to be at lower electrical potentials. So they're going to want to now be in this intracellular compartment because it's got the lower electrical potential, and they're not going to want to be in the extracellular compartment because it's got the higher electrical potential. Okay, so these potassium ions aren't going to want to move out as much, really. So this movement of potassium across the membrane is going to get smaller. So this movement is going to get smaller. So I'll draw it getting smaller. How shall I do that? I'll do it in this blue pen. So this is going to get smaller. Meanwhile, the movement of sodium into the cell is going to get bigger because the electrical gradient is now driving sodium into the cell. And I should stress that this electrical potential difference across the membrane is built up ridiculously quickly and by hardly any ions actually moving. So as far as we're concerned, the concentrations of sodium and potassium inside and outside the cell have not changed because the number that move is tiny, absolutely tiny, factors of billions and billions smaller than the concentrations we're actually dealing with. So for all intents and purposes, we can model the concentrations as though they are static. We can think of them as static. Okay, so it's not that this arrow gets smaller because the potassium is actually gradually moving into there, so the concentration gradient's getting smaller. No, that doesn't happen. What happens much, much quicker, it would happen, eventually it would happen, but what happens much quicker is this electrical potential starts building up. That happens really quickly. You hardly have to move any at all to get that. And that's what starts pulling the potassiums back, if you like, and stopping them from wanting to move out. Okay, so eventually what happens is that the movement of sodium in gets big enough, i.e. eventually what happens is this electrical potential difference across the membrane gets big enough that the movement of sodium into the cell is going to exactly match the movement of potassium out of the cell, and at that point you will reach an electrical equilibrium, because if the movement of sodium in is matching the movement of potassium out, then you're not moving any net positive charge across that membrane, so you're not going to change the electrical potential at all anymore, and that voltage at which you reach that is negative 65 millivolts for the initial concentrations of sodium and potassium and the relative permeabilities of sodium and potassium across this membrane. Okay, right. Now, we have reached an electrical equilibrium now, but we have not reached an ionic equilibrium because we still have a net movement of sodium in and we have a net movement of potassium out. So you're overall going to bring sodium into the cell and deplete the potassium out of the cell. So what you have is a pump, a sodium-potassium pump. And what colour should I colour this in? So you have this sodium-potassium ATPase, which is also in the membrane, which basically extrudes free sodium ions out of the cell and in exchange brings two potassiums into the cell, like so. And basically, do not think that this pump is what creates the electrical potential difference across the membrane. I've shown you what creates the electrical potential difference across the membrane. It is not this sodium-potassium pump. The sodium-potassium pump's role is to reverse the movement of ions and not to build up the electrical potential difference. So this is the sodium-potassium ATPase, or the sodium-potassium pump, as people often refer to it as. Now, it is electrogenic, meaning that it does move free sodium ions out and two potassiums in, and therefore it does move a net positive charge out. But the contribution of that to the actual electrical potential difference across the membrane is tiny. So this pump's main role is to reverse the movement of ions across this membrane, rather than to establish the resting membrane potential across the cells. Right. Okay, so this pump requires ATP in order to operate. So every time it moves 3 sodiums out and 2 potassiums in, it hydrolyzes a molecule of ATP to a molecule of ADP. So here it will make that into ADP. So this is ADP, and obviously also an inorganic phosphate comes off in that reaction as well, so PI goes over there. Right, so if ATP goes down in the cell, this pump is going to become less active. So what happens when that becomes less active? Well, what was its role? Its role was to remove the sodium and bring the potassium back in. So if it stops doing that, then what's going to happen is that these concentration gradients across the cell membrane are going to gradually change, basically. Sodium is going to start moving into the cell, and potassium is going to start moving out of the cell. So the ionic gradients across the membrane start to change, basically. Okay, now another important, so that's one of the effects of ATP going down. Now another important role of ATP in the cell, in the axon terminal, is with this plasma membrane associated calcium ATPase over here. So plasma membrane associated calcium ATPase. Okay, so this calcium pump, this basically extrudes a single calcium ion, and in exchange for the extrusion of calcium ions, what has to happen is that ATP has to be broken down. So this pump also breaks down ATP in exchange for removing a calcium ion. Okay, so if ATP goes down, firstly, this plasma membrane associated calcium ATPase stops extruding calcium. Secondly, why did I tell you about this? Well, this doesn't look to have anything to do with calcium, but think it does. What was the other thing which extruded calcium? The other pump involved in extruding calcium basically was a sodium-calcium exchanger. It brought 3 sodium ions into the cell in exchange for a single calcium ion going out of the cell. And it relied completely and utterly on the sodium concentration gradient across the cell. If the sodium-potassium pump stops working, then these leaky sodium channels are going to let sodium come into the cell, and you're going to get a net movement of sodium into the cell. So the gradient of sodium across the cell membrane is going to go. If the gradient of sodium across the membrane is lost, then the sodium-calcium exchanger goes down as well. So both of our mechanisms for extruding calcium go, and those are the things that are keeping calcium at a low level within this axon terminal of around 100 nanomolar. Okay, so basically, if ATP goes down, calcium is going to end up going up in the cytoplasm because both of the mechanisms for removing it have been lost, and there's always going to be some leak of calcium into the cell membrane, into the axon terminal. You can't stop calcium coming in, basically. There's always going to be some calcium leaking back into the axon terminal if you've got that sort of a concentration gradient. So you always need to have these extrusion mechanisms for removing the calcium back again. And basically, if ATP goes down in the cell, both of the extrusion mechanisms go down, and you've got no way of removing calcium from the cytoplasm again. Okay, and that's going to lead to excitotoxicity, basically. So remember, the extracellular calcium concentration is around 1.5 millimolar. So that's why you always have some leak. You're always going to get some calcium ions forcing their way back into here. Okay, so in the next video we'll talk about what this rise in calcium level, which is going to result because of the loss of function of these extrusion mechanisms, is going to cause. So calcium has gone up is the point of the story that we've got to so far.